Hello everybody, today we'll be going over CSES problem number 1707, graph girth. We have an undirected graph and we need to determine the girth, which is the length of the shortest cycle. Our input is n, the number of nodes, and m, the number of edges. After that, we have m lines in the form of a and b, which indicates that there is an edge between these two nodes. For output, we want to print the length of the shortest cycle if it exists, and if not, we print -1. Let's take a look at our sample case. We have 5 nodes and 6 edges. The edges are between 1 and 2, 1 and 3, 2 and 4, 2 and 5, 3 and 4, and 4 and 5. We can see that the shortest cycle is made up of the edges between nodes 2, 4, and 5, aligning with the output of 3. Note that for undirected graphs, cycles need to contain at least 3 nodes, meaning going back and forth between 2 nodes is not a valid cycle. Let's take a look at some preliminary observations we can make. A cycle has 3 or more nodes ending up in a loop, and we want the shortest cycle. The graph does not need to be connected, so we need to make sure every node is processed. Next, let's get into some observations that will help us solve this problem. We have 2 tasks, detecting a cycle and calculating the length of it. To detect cycles, we need to traverse this graph. Conveniently, to find the length of the shortest cycle, we can use information regarding shortest path during the same traversal. This problem ends up being a shortest path problem and the edges are unweighted, so that should lead to the conclusion of using BFS. Let's now get into how we use BFS. A graph with no cycles means that each node has only one parent at most. If we reach a node that already has a parent assigned to it, we thus have a cycle. Let's take a look at a quick example to show what I mean. Suppose we have 3 nodes, U, V, and O, where O is the starting node of the BFS. So the parents of U and V are set to O. However, when the BFS arrives at node U, it sees that both O and V have already been visited. O is U's parent, so we disregard that part to avoid one-edge cycles, but U is not V's parent, so we thus have a cycle. Since we used BFS to calculate the shortest path to each node, we can add up the distances from the start of the BFS to these nodes plus 1 to get the cycle length. If the graph were larger, all the nodes from O to U and O to V would be part of the cycle. We have the plus 1 because there is an edge between U and V that we need to count as part of the cycle. Now let's take a look at how the BFS works on our sample case. We start at node 1 and mark it with a distance of 0. The BFS then goes to nodes 2 and 3, marking them with distances of 1. After that, from node 2, we reach nodes 4 and 5 with distances of 2. Node 3 will then try to visit node 4, but node 4 already has a different parent in 2. Thus, we have a cycle and compute the length of it to be 4. Remember that we have to check that 3 is not 4's parent because otherwise we would be getting a one-edge cycle where 2 nodes end up going back and forth. Node 4 will then try to visit node 5, but node 5 already has a different parent in node 2. Thus, we have a cycle and compute the length of it to be 5. Our BFS from node 1 reports a minimum cycle length of 4. However, the output tells us that the answer should actually be 3. This difference is because starting from node 1 assumes that node 1 is part of this shortest cycle. To fix this, we can loop through all nodes and find the shortest cycle that passes through each one. This also addresses the issue regarding disconnected components as each node is guaranteed to be processed. So let's take a look at the BFS starting from node 2. It marks nodes 1, 4, and 5 with distances of 1. Node 3 is then marked with a distance of 2. 4 will then try to visit 3, which has a different parent, so we can compute the cycle length to be 4. 4 will then try to visit 5, which also has a different parent, so we can compute this cycle length to be 3, which is now correct with the output. In the actual code, we'd repeat the BFS for the rest of the nodes. Finally, let's look at the implementation. We read an n, m, and the edges. We construct the graph based on the edges, and then we loop through the n nodes. We start BFS from each one, and if a node is revisited from a node that is not its parent, we have a cycle. We then need to update the minimum length of the cycle if it is shorter than a past one. Finally, if a cycle exists, we want to output the minimum length, and if not, we return -1. This approach has a time complexity of O of n times n plus m, as BFS has a runtime of n plus m, and we conduct it once for each of the n nodes. It has a memory complexity of O of n plus m, as we need to store the adjacency list. That's all for the general explanation. Now I'll get into language-specific solutions for C++, Java, and Python. Let's take a look at the C++ implementation for this problem. We define n and m and read them in. After that, we'll define our adjacency list and then read in our m edges. We'll read in the edge, and then we'll push it into the adjacency list. After that, we'll loop through the n nodes and begin BFS from each node. Now let's take a look at how our BFS works. First, we'll define our distance vector, which stores the distance from every node to the start. After that, we have our parent vector, which stores every parent of every node. We'll create our queue and then push the starting node into the queue. We then have a variable to keep track of the length of the minimum cycle going through the starting node. While the queue is not empty, we'll take out the current node and then pop it from the queue. We'll loop through the current node's neighbors, and if the node has not been visited, we mark its parent as the current one and then update its distance to the current distance plus 1, and then we push it into the queue. However, if the neighbor has been visited and is not the parent of the current cell, then we need to update the minimum cycle with our calculation of the distance to the current cell plus the distance to the next cell plus 1. After that, we'll return the length of the minimum cycle, so our result in main will receive that minimum length. Finally, we'll output the minimum length if it exists. That's all for the C++ explanation. Now I'll get into the Java code. Now let's take a look at the Java code. Note that this approach TLEs on test case number 8. We'll define our variables n and m and read them in. After that, we'll define our adjacency list and then we'll read in our m edges. We'll zero index them for convenience and then we'll add them to the adjacency list. Then, we'll loop through the n nodes and then find the length of the shortest cycle that passes through each node. We'll do this using BFS, whose implementation we'll look at now. For the BFS, we create a distance array and set them all to unvisited. After that, we set the starting distance to 0. After that, we'll create our parents array, which stores the parent of each node, and we'll initialize them all to -1. We'll create our queue for BFS, and then we'll push the starting node into the queue. Then we'll create a variable to store the length of the minimum cycle that passes through the starting node. While the queue is not empty, we'll take out the current cell and loop through its neighbors. If its neighbor has not been visited, we update its parent to the current cell, update its distance to the current distance plus 1, and then push it into the queue. If it has been visited and it's not the parent of the current cell, it means we have a cycle. We need to update the length of the minimum cycle by taking the current distance plus the neighbor's distance plus 1. After the BFS, we'll return the length of the minimum cycle so that if a cycle exists, the result variable back here will store the length of the shortest one. At the end, we'll output the length of the shortest cycle if it exists, and if not, we'll print -1. That's all for the Java code. Now let's take a look at the Python solution. Note that using the default interpreter TLEs on a number of cases, and even using PyPy still TLEs on case number 8. We'll define our variables n and m and read them in. We'll then define our adjacency list and then read in our m edges. We'll zero index them for convenience and then add them to the adjacency list. We'll then loop through our n nodes and then find the length of the shortest cycle that passes through each node using BFS. Now let's take a look at our BFS. We'll create a distance array and then set the distance from the starting node to 0. We'll then create our parents array, which stores the parent of each node. We'll create our queue for BFS and then add the starting node into the queue. We'll then create a variable that stores the length of the minimum cycle that passes through the starting node. While the queue is not empty, we'll read in the current node and then loop through its neighbors. If the neighbor has not been visited, we set its parent to the current node and then update its distance to the current distance plus 1, and then we'll add it to the queue. Otherwise, if the neighbor is not the parent of the current cell, it means we have a cycle, so we need to calculate the length of the cycle by taking the current distance plus the neighbor's distance plus 1. After the BFS, we'll return the length of the shortest cycle, so result should store the length of the shortest cycle after looping through all n nodes. If no cycles exist, then we'll print -1, otherwise we'll print result. That's all 3 language implementations done. Thank you for watching this video.